Imagine for a moment the incredible challenge of creating a detailed map of your city while soaring through it at the astonishing speed of 828,000 kilometers per hour. This mind-bending scenario isn't just a thought experiment. It's the reality that astronomers face every single day as they work to map the cosmos. Our solar system isn't static. It's racing through space at breathtaking velocities, making the task of measuring and mapping the stars an extraordinary feat of human ingenuity. Welcome to the captivating world of astrometry, the sophisticated science of measuring and mapping the stars. The journey we're about to embark on will take us through some of humanity's greatest achievements in understanding our cosmic neighborhood. We'll explore how our ancestors, armed with nothing but their keen eyes and primitive tools, first began the monumental task of mapping the night sky. From these humble beginnings, we'll venture into the present day, where cutting-edge technology allows us to measure stellar distances with unprecedented precision. You'll discover why knowing the exact positions of stars isn't just an academic exercise. It's absolutely crucial for the future of space exploration and our understanding of the universe. The story of astrometry is also a testament to human perseverance and innovation. We'll uncover how this field has led to groundbreaking discoveries that have fundamentally changed our understanding of the cosmos. From finding distant planets orbiting other stars to mapping the structure of our own galaxy, astrometry has opened windows into the universe that our ancestors could only dream of. Before we dive deeper into this cosmic adventure, I invite you to join our growing community of space enthusiasts and curious minds. Together, we'll explore the mysteries of the universe and uncover the fascinating methods astronomers use to create precise maps of the cosmos. Have you ever gazed up at the night sky and wondered how we know the exact location of each twinkling star? How do we track their movements across the vast cosmic ocean? These are just some of the intriguing questions we'll answer as we journey through the remarkable science of astrometry. Think about it. Every time you look up at the night sky, you're witnessing a cosmic dance that astronomers have learned to measure with incredible precision. Despite the fact that everything, including our own planet and solar system, is in constant motion. This is the essence of astrometry, where the seemingly impossible task of mapping moving objects from a moving platform becomes possible through human ingenuity and technological innovation. The remarkable journey of astrometry stretches back over 2 millennia to ancient Greece, where a visionary astronomer named Hipparchus would forever change our understanding of the night sky. In approximately 129 BCE, on the island of Rhodes, Hipparchus undertook what would become one of humanity's most ambitious scientific projects, creating the first comprehensive catalogue of the stars. Armed with nothing more than his naked eyes and rudimentary instruments like the gnomon and armillary sphere, Hipparchus meticulously observed and recorded the positions of 850 stars. His tools, though primitive by today's standards, were ingeniously designed. The gnomon, a simple vertical stick, allowed him to measure the sun's height and the length of shadows, while the armillary sphere, a complex framework of rings representing celestial circles, helped him determine stellar positions with remarkable accuracy. What makes Hipparchus's achievement truly extraordinary was his introduction of a mathematical system to describe stellar positions. He developed a method of locating stars using 2 coordinates, similar to our modern system of celestial latitude and longitude. This revolutionary approach allowed him to record stellar positions with an accuracy that would remain unmatched for nearly 1,500 years. Hipparchus also made another groundbreaking discovery while comparing his observations with earlier Babylonian records. He noticed that the positions of stars had shifted slightly over the centuries, leading him to discover the precession of the equinoxes, the gradual shift in Earth's rotational axis over a 26,000-year cycle. This discovery demonstrated that even the seemingly fixed stars were part of a dynamic, changing cosmos. The precision of Hipparchus's measurements was so remarkable that when Ptolemy created his own star catalogue almost 300 years later, he relied heavily on Hipparchus's data. In fact, modern astronomers have found that many of Hipparchus's position measurements were accurate to within 1 degree, an astounding feat considering he had no telescopes or modern measuring devices. This ancient Greek astronomer's work laid the foundation for all future stellar cartography. His systematic approach to measuring and recording stellar positions established astrometry as a precise science, setting standards that would influence astronomers for generations to come. From the medieval Islamic astronomers who built upon his work, to the Renaissance scientists who used his methods to challenge our understanding of the cosmos, Hipparchus's influence on astronomical science cannot be overstated. The legacy of Hipparchus reminds us that the human drive to understand our place in the universe is timeless. His work represents not just humanity's first systematic attempt to map the stars, but also demonstrates how careful observation, precise measurement, and mathematical thinking can unlock the mysteries of the cosmos. Principles that remain at the heart of modern astrometry. At the heart of astrometry lie 3 fundamental measurements that form the cornerstone of our understanding of the celestial sphere. Each of these measurements works in concert with the others to give us a comprehensive, 3-dimensional view of our cosmic neighborhood. Let's begin with stellar positions, the most basic yet crucial measurement in astrometry. Just as we use latitude and longitude to pinpoint locations on Earth, astronomers use a celestial coordinate system to map the exact position of stars in the sky. This system, known as the celestial sphere, uses right ascension and declination, similar to longitude and latitude, to create a precise cosmic address for each star. The level of precision required is staggering. Modern instruments can measure stellar positions down to milliarc seconds, equivalent to measuring the width of a coin on the moon as seen from Earth. The second fundamental measurement, proper motion, adds the dimension of time to our understanding of the cosmos. While stars may appear fixed in the night sky during a human lifetime, they are actually moving through space at incredible speeds. Some stars move faster than others. Barnard's star, for instance, travels across our sky at the apparent speed of the width of the full moon every 180 years. Measuring proper motion requires incredible patience and precision, often involving observations spanning decades or even centuries to detect these subtle movements. Parallax, the third pillar of astrometric measurements, is perhaps the most ingenious method astronomers use to determine stellar distances. This technique takes advantage of Earth's orbit around the Sun to create a baseline for triangulation. As Earth moves from one side of its orbit to the other, a distance of about 300 million kilometers, nearby stars appear to shift position slightly against the background of more distant stars. The amount of this shift, called parallax angle, allows astronomers to calculate the star's distance with remarkable accuracy. To understand parallax in a tangible way, try this simple demonstration. Hold your thumb at arm's length and look at it against a distant background, like a wall or window. Close one eye, then switch to the other eye while keeping your thumb steady. You'll notice your thumb appears to jump position relative to the background. This same principle, scaled up to astronomical distances, allows us to measure how far away stars are from Earth. The closer the star, the larger this apparent shift will be. The evolution of technology has revolutionized how we make these measurements. From Hipparchus's naked eye observations to modern space-based telescopes like Gaia, our ability to measure these 3 fundamental aspects of stars has improved dramatically. Today's instruments can measure stellar positions with unprecedented accuracy, detect proper motions of stars thousands of light years away, and calculate parallaxes for millions of stars simultaneously. This incredible precision has led to groundbreaking discoveries. For instance, by carefully measuring proper motions, astronomers have discovered that stars don't move randomly through space, but often travel in streams, remnants of ancient star clusters torn apart by our galaxy's gravitational forces. Precise parallax measurements have allowed us to create the most accurate three-dimensional maps of our galactic neighborhood ever made, revealing previously unknown structures in the Milky Way. The beauty of these three measurements lies in how they complement each other. Together, they give us a complete picture of a star's location in space, its movement through the cosmos, and its distance from Earth. This three-dimensional understanding is crucial not just for mapping our galaxy, but for everything from planning space missions to understanding the evolution of the universe itself. The advancement in measurement precision continues to amaze astronomers and space enthusiasts alike. What started as simple angle measurements using primitive tools has evolved into a sophisticated science capable of mapping billions of stars with extraordinary accuracy. The questions these measurements raise about the structure of our galaxy, the existence of dark matter, and the nature of stellar evolution continue to drive innovation in astronomical measurement techniques and technology. The scientific impact of astrometry has been nothing short of revolutionary, fundamentally transforming our understanding of the universe and our place within it. Through incredibly precise measurements and systematic observations, this field has led to some of astronomy's most significant discoveries. One of astrometry's most remarkable contributions has been in the field of exoplanet discovery. By detecting the subtle wobble of stars caused by orbiting planets, astrometric measurements have helped identify thousands of worlds beyond our solar system. This technique, known as the astrometric method, is particularly powerful because it can detect planets that other methods might miss. For instance, the European Space Agency's Gaia mission has not only confirmed previously discovered exoplanets, but has also revealed numerous new candidates by measuring stellar movements with unprecedented precision, down to microscopically small, angular shifts in a star's position. The mapping of our Milky Way galaxy represents another triumph of astrometric science. Through precise measurements of stellar positions and motions, we've discovered that our galaxy is far more complex and dynamic than previously thought. We now know that the Milky Way isn't just a simple spiral galaxy. It's a sophisticated structure with multiple arms, a central bar, and several distinct stellar populations. Astrometric surveys have revealed previously unknown features like the Gould Belt, a ring of young stars and gas clouds that may have formed from an ancient collision with another galaxy. Perhaps one of astrometry's most profound contributions has been in providing evidence for dark matter. By measuring the motion of stars and gas clouds in galaxies, astronomers noticed that these objects move faster than they should, based on the visible matter alone. This led to the groundbreaking conclusion that some invisible form of matter, dark matter, must exist to provide the extra gravitational force needed to explain these movements. Astrometric measurements of stellar velocities in globular clusters and dwarf galaxies have further strengthened this evidence, showing that dark matter is essential to our understanding of cosmic structure. The creation of detailed three-dimensional maps of our cosmic neighborhood represents another remarkable achievement. Modern astrometric missions like Gaia have measured the positions, distances, and motions of over 1 billion stars with unprecedented accuracy. This has allowed us to create the most detailed map of our galaxy ever made, revealing previously unknown stellar streams, clusters, and structures. These maps have shown us that the Milky Way's disk is warped and rippling, possibly due to past galactic collisions, and have helped us identify the remnants of ancient galaxies that our Milky Way has absorbed over billions of years. Beyond these major discoveries, astrometry has also led to numerous other scientific breakthroughs. It has helped us understand stellar evolution by allowing us to precisely measure the distances to star clusters, enabling accurate age determinations. It has revealed the complex dynamics of multiple star systems, showing how binary and triple star systems interact and evolve. The field has even contributed to fundamental physics by helping test Einstein's theory of general relativity through precise measurements of stellar positions during solar eclipses. The impact of astrometry extends into our understanding of galactic archaeology, the study of our galaxy's formation and evolution. By measuring the motions and chemical compositions of millions of stars, we can trace their origins and reconstruct the violent events that shaped our galaxy. This has revealed evidence of past galactic mergers and shown how the Milky Way has grown by consuming smaller galaxies throughout its history. Looking to the future, astrometry continues to push the boundaries of our knowledge. New missions and more precise measurements promise to reveal even more exoplanets, better define the distribution of dark matter, and perhaps uncover entirely new phenomena that we haven't yet imagined. The field's ability to make increasingly precise measurements ensures that it will remain at the forefront of astronomical discovery for generations to come. The practical applications of astrometry extend far beyond the realm of pure scientific research, playing a vital role in numerous aspects of space exploration, navigation, and our understanding of cosmic phenomena. These real-world applications demonstrate how this ancient science continues to shape our modern world and future space endeavors. Space navigation represents one of astrometry's most critical applications. Just as ancient sailors used the stars to navigate Earth's oceans, modern spacecraft rely on precise stellar measurements for navigation in space. This celestial positioning system, often called celestial navigation, requires incredibly accurate star catalogues created through astrometric measurements. When spacecraft venture into deep space, they use specialized cameras to capture images of stars and compare them with these catalogues to determine their exact position and orientation. This technique proved crucial during missions like Voyager and New Horizons, where traditional GPS systems couldn't function due to the vast distances involved. In the realm of satellite positioning, astrometry plays an indispensable role. Earth-orbiting satellites, whether they're communication satellites, weather monitors, or scientific observatories, require precise positioning to function effectively. Astrometric measurements help determine and maintain these satellites' orbits with remarkable accuracy. For instance, when launching new satellites, engineers use detailed star maps to ensure proper alignment and positioning. This precision is particularly crucial for geostationary satellites that must maintain exact positions relative to Earth to function properly. The planning of interplanetary missions represents another crucial application of astrometric science. When plotting courses for spacecraft to reach other planets or celestial bodies, mission planners must account for the complex gravitational interactions between celestial bodies, their movements and positions over time. Astrometric data provides the foundation for these calculations. For example, when planning the New Horizons mission to Pluto, NASA relied on precise astrometric measurements to plot a trajectory that would intercept Pluto nearly a decade after launch, requiring accuracy equivalent to hitting a golf ball from New York and making a hole-in-one in Los Angeles. Understanding our galaxy's future through astrometric measurements has practical implications for long-term space exploration and potential hazard assessment. By measuring the proper motions of stars and other celestial objects, astronomers can predict future close encounters between stars and our solar system, identify potentially hazardous asteroids, and even anticipate the Milky Way's eventual collision with the Andromeda galaxy. This information is crucial for long-term space mission planning and understanding potential risks to Earth from cosmic events. The applications of astrometry also extend to timekeeping and calendar systems. The precise measurements of Earth's rotation and its relationship to distant stars help maintain accurate time standards used worldwide. This has practical implications for everything from GPS systems to international commerce and communications. In the field of climate science, astrometric measurements help us understand Earth's orbital variations and their impact on long-term climate patterns. By precisely measuring Earth's position relative to other celestial bodies, scientists can better understand and predict how astronomical factors influence our planet's climate cycles. Defense and security applications also benefit from astrometric science. Military satellites and reconnaissance systems rely on precise stellar positioning for accurate operation. Additionally, space situational awareness, tracking artificial satellites and space debris, depends heavily on astrometric techniques to maintain safety in increasingly crowded Earth orbits. Looking to the future, astrometry will play an essential role in ambitious space exploration goals. As we plan missions to Mars and beyond, the need for precise navigation and positioning becomes even more critical. The development of autonomous navigation systems for spacecraft will rely heavily on astrometric data, allowing vessels to determine their position and adjust their trajectory without constant communication with Earth. Commercial space ventures are increasingly relying on astrometric data for their operations. From space tourism to asteroid mining initiatives, precise stellar measurements and positioning are essential for safe and successful operations. As the commercial space sector continues to grow, the practical applications of astrometry will become even more vital. As we conclude our fascinating journey through the science of astrometry, let's take a moment to appreciate the incredible achievement that this field represents. When you next look up at the night sky, remember that each twinkling point of light has been meticulously measured, tracked, and documented with astonishing precision. What began with Hipparchus counting stars by eye has evolved into a sophisticated science capable of measuring stellar positions with accuracy equivalent to spotting a grain of sand on the moon from Earth. This precision isn't just a testament to human ingenuity, it's a gateway to understanding our place in the cosmos. Through astrometry, we've discovered that we're part of a vast, dynamic universe where everything is in constant motion. Our solar system races through space, stars dance across the celestial sphere, and galaxies perform a cosmic ballet that we can now measure and predict with remarkable accuracy. Think about the journey we've taken together, from understanding how ancient astronomers first mapped the stars, to exploring the cutting-edge technology that allows us to detect planets around distant suns. We've learned how parallax helps us measure cosmic distances, how proper motion reveals the dynamic nature of our galaxy, and how these measurements contribute to everything from space exploration to our understanding of dark matter. The story of astrometry is far from over. As technology advances and our measurements become even more precise, we stand on the brink of new discoveries. Will we find more Earth-like planets around nearby stars? Will we better understand the dark matter that shapes our galaxy? Will we uncover new phenomena that we haven't yet imagined? These questions await future generations of astronomers, armed with ever more precise measuring tools. Whether you're a casual stargazer or an aspiring astronomer, you're now part of this ongoing story of discovery. Every time you look up at the night sky, you're not just seeing random points of light. You're seeing a carefully mapped cosmic neighborhood that continues to reveal its secrets through the science of stellar measurement. I invite you to continue this journey of cosmic discovery with us. Join our community of space enthusiasts, where we explore the wonders of the universe together. By subscribing to Exploring the Universe, you'll be part of a growing group of cosmic explorers who share your fascination with the stars. Each week, we'll delve into new astronomical mysteries, explore cutting-edge discoveries, and continue to unravel the secrets of our cosmic home. Remember, every great astronomical discovery began with a simple measurement, a star's position, a subtle movement, a slight dimming of light. As we continue to measure and map the cosmos with ever-increasing precision, who knows what wonders we'll uncover next? Be part of this exciting journey by joining our community today, and let's explore the frontiers of space together. The universe is vast, but through the precise measurements of astrometry, we're making it just a little bit more knowable, one star at a time. Subscribe now to Exploring the Universe, and let's continue this amazing journey of cosmic discovery together.